I'm Jay Harbert. I'm an airframe and power plant mechanic, and I instruct here at Alabama Aviation College. One of the subjects I teach is composites and the terminology and the skill sets necessary to build, inspect, and repair composite structures. But I think with any technical pursuit, the very first step in learning something new is to kind of establish a good foundation, and the purpose of this lesson today is to establish what defines a composite, as well as some common terms that you would need to know in order to work within the composite technology, the composite repair and manufacturing environment. So let's begin at the beginning. Composite, by definition, is two or more materials that are combined together in such a way that they create a new material, yet they still retain their individual identity. Now, if you've studied metals and metallurgy in your program, that's going to sound very familiar, because when we alloy metals together, we're doing a very similar thing, but the definitions are different. And here's the key point you need to keep in mind. When we alloy metals together, we're taking different metals and blending them to get a desired result. So we're going to create a metal by a combination of differing metals and elements. But when we alloy something, it all goes into the pot, blends together, and it creates something different, but each of those metals lose its own individual identity. So an alloy is similar in definition, but with a composite, each part keeps its own identity. You say, well, what do you mean by that, Jay? Well, it's simply this. If you cut a piece of aluminum alloy and look at it closely, you won't see the copper or manganese or magnesium or whatever other element that was added. They all blend and take on the same appearance. With a composite, however, if we cut that part, zoom in real close and look, what you'll see is that you can see the carbon is still carbon, or the fiberglass is still fiberglass, or in some cases the Kevlar or aramid fiber is still the aramid fiber. So to look at that definition, that forms a foundation that we can build upon. And the definition, once again, is when we blend two or more materials to create a new material, yet each individual component still retains its identity. That's our basis, and that's where I want to start this lesson. In general, composite is hot technology. They're looking for people that can repair composites, that can manufacture composites, also inspect them. But although it's hot technology, it's not new technology. If you look back in human history and you think, well, when did composites first come onto the scene, so to speak, you have to actually look back thousands of years. Let's take a look at one of the first composites. Early on in human history, people needed to be out of the element, out of the heat, out of the cold, out of the rain, and most natural materials could create a hut that would last not necessarily all that long, and it didn't always do a great job. But let's think about that definition. What if we went down to a riverbank and we found some clay, good old sticky clay, and we gathered some of it. Then we went up to the edge of the desert or further away from that river and we found some sand, loose sand. Then we looked and found some grass. We take the grass, we break it into small pieces, we mix it, the sand and clay together. We form it, we press it into a form, we let it lay out in the hot sun and dry, or cure is the term we use in composites. Then you dump that out and what you have is a brick, something that's more durable. You could build a better structure, it could withstand stronger weather and keep the rain off of your head. Now if you think about what I just described and compare it to that definition, didn't we blend two or more things together to create a new product? Yes, we did. And if you broke a brick, could you still see the straw? could you still see that old red clay like we have here in Alabama? Could you see the brighter, whiter sand involved? You absolutely could. Therefore, the first composites were actually manufactured thousands of years ago to meet a desperate need, which was a need for shelter, a basic need. Now, with that as a foundation, understanding what a composite is a big step forward toward understanding what's going on in here in front of me. But we also need to understand, why would we choose to do it? Airplanes were first built out of wood and fabric. Then we transitioned over to aluminum, and now we're transitioning more and more toward composites, to the point that up to 80% of some aircraft now are composite materials. Why do we do that? Why is a composite such a desirable material? Well, there's several reasons, but let's examine the top few. For one thing, a composite material is a stronger material than many metallic structures, but at a much less weight. The typical savings of a piece of structure, if we make one out of metal, one out of composite, typically composites are going to be at least 20% lighter at the same strength, or possibly stronger, than the metallic structure. That's a big bonus. If you look at the aircraft world, airplanes are paid to haul people or things, and the lighter that we can build the airframe, the more we can put in that aircraft, which is actually going to generate revenue, which is the whole point of the effort. So composites are stronger and lighter. That alone would be a pretty motivating factor to choose composite materials over metallic structures. Metallics are also more durable in some ways. Metallic structures, if they're stressed or flexed or move, they tend to work harden over time. I always compare it, and some of you may have never done this, but coat hangers used to be made of mild steel rods, and if you ever wanted to cut one and didn't have a way to cut it, you could just simply start bending it at one point, and if you kept doing that, eventually that hanger would break right there. It broke because it work hardened. Work hardening is a process of making a metal harder at room temperature, and as the metal gets harder, it gets more brittle. And it'll reach a point that it becomes so brittle that it'll break or crack. Composites tend to resist that. So they can fly and withstand the loads and stresses that are required for aircraft parts for many, many more cycles or years without reaching that state that they've work hardened to the point that they no longer have a service life. Lighter, stronger, more resistant to fatigue. Sounds like a winner so far, but we can add to that even further. Composites don't suffer from corrosion like a lot of metallic structures do. In aviation, marine, building, just about all aspects of a machine or anything that we build and we use metals, we have to put in some time, effort, and money into maintaining those structures by replenishing or refinishing surface coatings, adding chemicals to make them more resistant to rusting or corroding. Composite structures do not have those weaknesses. So we have no worries for the most part about corrosion, and we don't have near the inspection requirement as we do for metallic structures. For those that are operating aircraft, that is a major money savings opportunity, because we're not paying people to go take things apart to look for corrosion. That's a major expense on a fleet of aircraft, especially if you calculate it over the lifetime. So we're lighter, we're stronger, we're more fatigue resistant, we're more corrosion resistant, and there's some other aspects as well. Aircraft parts need to be strong, but often they need to be flexible as well. Using composites and fiber science, a term that we'll look at a little closer, we can create a composite part that not only can carry the load, but it can be flexible enough that we don't cause cracks and other problems. Structures need to be strong, but they also need to be flexible, because if a structure is too rigid, we'll suffer from cracks, and that's not a good idea. So we can add that idea of building the part and kind of custom making it to meet the need of where it's going to go on the aircraft. One other big advantage is creating shapes. If I take a piece of flat metal and I want to create a complex shape, often that's going to require big, expensive, fixed equipment that's able to put tons of pressure on that piece of metal in order to form the shape. Now, to do that, we need machinery that creates tons and tons and tons of hydraulic pressure, which is generally large and expensive. Then we also have to spend a great deal of money creating the dies, a male and female die. We put the piece between them, and under tremendous pressure, we can squeeze and cause that metal to form into complex shapes. It works, and we've done that for many, many decades, but there's an easier way now. With composites, we can build lighter weight molds and eliminate the requirement for large, expensive, and complex fixed equipment. By building molds, we can shape parts into complex shapes, and here's another benefit: the parts can often be much larger, which leads to a lower parts count on whatever we're going to make. So once again, that's a big bonus. Rather than assembling hundreds of small parts, I may make only a dozen larger parts that have to be joined together. In doing so, you save labor, you save money, you increase the speed of manufacture. So if we look at that long list, that's why we like composites. Lighter, stronger, fatigue resistant, corrosion resistant, customizable strength and flexibility, and easier formation of large complex shapes. All those reasons add up to why composites are currently such a high demand field. Now, composites aren't perfect. If we never had a problem, I wouldn't be making this video, and we wouldn't have anybody doing any repair work. There are problems associated with composites, but they're so much fewer than with metallic structures, but we need to be well trained and informed to deal with those problems. One of the problems, and one of the most prevalent issues, is damage, impact damage. We make mistakes. We bump into these composites, it can damage them. Sometimes, although this is a much smaller percentage, there might be a manufacturer's flaw that shows up later in the service life of that composite part, and oftentimes it has to do with water intrusions or other liquids getting inside the part. So because there are some things that can harm composites, we need to be well trained and highly skilled in addressing and working on those composite parts. And that's what this introductory lesson is about, is to build that foundation so we can move forward into manufacturing, how to make these parts, inspection. There's many techniques that are used and you need to understand in order to do a good and proper inspection on that part. That ensures continued airworthiness and safety. And then finally, repair. To be able to go out and repair that part rather than having to replace a very expensive aircraft part. So this video, this effort, this lesson is going to move you through these steps to the point that we can start working toward manufacture. All right. In order to understand how we're going to go about making a composite part, we first need to look at what does it take to make the part? What materials are involved and what is their purpose? Well, there's primarily three things that we need to understand about a composite part. That is the fiber, that's the actual material that's used to make the part. Then the matrix system. A matrix system is simply a way of saying the resin or the chemicals that we're going to mix to hold those fibers together. And then finally, some core materials. These materials are added to composites to make parts thicker, but with a very low weight penalty, which is a pretty awesome trade-off. Thicker parts tend to be more rigid, so if we can use lightweight material to make a thicker part, we can get more strength with very little added weight. So of those three parts, the first part we should always take a look at is the fibers themselves. Understand that in a composite part, the matrix or resin is not there to provide strength. The cores don't necessarily add strength. The real strength is found within the fiber itself. And we're going to take a look at the three most commonly used fibers in those types of systems, because understanding the fibers and their characteristics is a very key part to understanding how to use and repair those fibers. So I'm going to get some fiber and we're going to examine some things so that you can get some general ideas of these three common fibers and their character.